All right, so we're gonna go over inverse functions here today. Talking about inverse functions. An inverse function, the way inverse functions act is the following. So an inverse function, what it does, we're gonna let f of x be one function. F of x equals y, our general notation for a function, f of x is y. All right, so x is the input. We put it into a function f, we get an output y. If we put this output into another function, calling it the inverse function, and this is the notation for inverse function, this -1 is not an exponent, it is the notation for an inverse function. So we take the inverse function of that output. Okay, so we have one function, we have an input x, we get an output y. If we put that output into its inverse function, we're going to get back the original input. That's what an inverse function does. It takes the output from an original function and turns it back into the input. That was the input to that original function. That's how inverse functions work. They do the reverse. This function does something to the input, changes it in some way, gives an output of y. Inverse function takes that output and reverses it and gives you the original input back. Now, graphically, we can look at this, and there is a visual component to this. If we draw a function here, I'm just going to create some points and connect them to create a function. So let's say we have the point -4, 0 over here. And then let's say we have the point 0, 2. And okay, so this is -4, 0. So that would be a 4 over here. Let's put a 2 in here and say 2, 4. 2, 4 is a point up here. And one more, let's go for 7. 4, 7 up here. Okay, so this fits the definition of a function. If I connect these dots, I'm going to see that passes the vertical line test. When we talked about the vertical line test, this passes the vertical line test. We're going to call this function f of x. That's our function f of x. Now, like we just talked about, the inverse function takes the output from the original function and gives you back the input. So if -4, 0 is on the f of x function, then 0, -4 is going to be on the inverse. 0, -4 is going to be on the inverse function. If 0, 2 is on f of x, then 2, 0 is going to be on the inverse function. If 2, 4 is on f of x, then 4, 2 is going to be on the inverse function. And if 4, 7 is on, then 7, 4 is also going to be on the inverse function. Now, if I connect these, we're going to see that it's a mirror image about this line y equals x. Okay, that's the line y equals x. So now if we look at this a little closer, we're going to see that, so I'm going to label these points, 7, 4, 4, 2, 2, 0, and 0, -4. So notice what's going on. -4, 0 is on f of x. This is my inverse function. Here. -4, 0 is on f of x. So 0, -4 is on the inverse. 0, 2 is on f of x. 2, 0 is on the inverse. 2, 4, 4, 2, 4, 7, 7, 4. This is always going to happen. Inverse functions are always going to be a mirror image about this line here, y equals x. And my drawing here isn't perfect, but you can see what's going on. It's a mirror image about that line. That's always going to be the case. So there's two things we want to be able to do in this section. We want to be able to, if we're given two functions, We want to be able to determine if they're inverses of one another. And given one function, we want to be able to find the inverse of that given function. Not always going to be able to find an inverse. Not every function has an inverse. We'll talk about that after we go through those two questions. So, first question, let's say we're given two functions. We're given f of x is 4x plus 9, and a second function g of x, we'll say is x minus 9 over 4. So we're given these two functions, and the question is, are these inverses of one another? Are these inverses of one another? That's what we want to determine. So to determine that, we're going to use our knowledge of composition of functions. So like we said, if this is f of x, it gives this output. Now, if we take that output and put it into this function, and we get back the original input of x, that's going to show that they're inverse functions, but it has to work in both ways. Okay, we have to find f of g of x and come up with x, and we have to find g of f of x and come up with x. It has to work in both directions. So we're going to use composition. So our answer, first we'll compose f with g. It has to work in both directions. So if you calculate this and it's not equal to x, you're done. They're not inverses of one. But if this comes out to be x, then we do the other direction of the composition. And if they both equal x, then yes, the answer to the question is yes, they are inverses of one. So first we'll do this. We're going to let this function, x minus 9 over 4, be the input to the f function. So the f function says take the input, multiply it by 4, and then add 9 to it. So that's what we're going to do here. We're going to take the input and multiply it by 4, and then add 9 to it. And as we can see here, you can think of this as 4 over 1. If you'd like, to make it easier, you can see that the 4 over 4 just equals 1. So we get 1 times x minus 9. It'll leave us with x minus 9 plus 9. So we do get the x that we were hoping to see. If we got anything other than x here, our answer is no. Since we did get x here, now we're going to check the other direction and say, what is g of f of x? So now we're going to let this function be the input to this function. So now we're going to say, what is g of 4x plus 9? So the g function says take the input, subtract 9 from it, and then divide the result by 4. So that's what we're going to do here. We're going to take 4x plus 9, the input. We're going to subtract 9 from it, and we're going to divide by 4. And again, if you look at this, the 9 and the 9 cancel out. We're left with 4x over 4, which does give us the x that we want to see. Since both of them come out to be x, the answer becomes yes. They are inverses of one another. Okay? So given two functions, question being, are they inverses of one another? Composed in one direction. If you get anything other than x, your answer is no. If you get an x here, then you're going to compose in the other direction. If both of them give back the original input, then your answer is yes. They are inverses of one another. Okay, so that is one thing you'll be expected to do in this section. Given two functions, determine whether they are inverses of one. Next task is when you're given one function and you're asked to find the inverse of that given one function. So let's say we're given the function f of x is x cubed minus 1. All right, and we are asked to find the inverse. So the question now is find the inverse function of that, if possible. If possible. We'll get to the possible in a minute after we do this. I'll show you what functions have inverses and how to tell whether a function has an inverse. So here the way to answer this is first, so a couple of steps. First step, we're going to rewrite the given function in terms of x and y. And it can be any two variables, but generally we use x and y to explain them. So we have this function here. We're just going to rewrite this. Instead of f of x, we're going to call it y. Because we know f of x and y are the same. Y is the output of the function. F of x is the output of the function. So we rewrote in terms of x and y. So second step, we're now going to switch the x's and y's. Switch x's and y's. So wherever you see an x, you're going to put a y. Wherever you see a y, you're going to put an x. So we're just switching here. We're going to make this an x, and we're going to make this a y. So now we have x equals y cubed. All right, now third step. Let's come over here and say third step. We're just going to solve that resulting function for y. We're going to solve it for y. Over here. So we're going to take this, which we had as x equals y cubed minus 1, and we're just going to solve this for y. So we're going to add 1 to both sides. We know how to solve an equation. And we know that, we want y to the first over here, so we're going to remember our property of exponents. It says this. All right, and we're going to ask ourselves, what do we need to multiply 3 by to get 1? And the answer is 1/3. Right? So we're going to raise both sides of this equation to the 1/3 power. Raise the left side to the 1/3. We're going to raise the right side to the 1/3. And when we do that, we're going to end up with x plus 1 to the 1/3 equals y. And that's our inverse function. That is the inverse function. That's our answer. Now, if we doubt any of that, we can always check it by using the same technique that we used earlier, right? So now I have my f function here, and I've come up with what I hope is the correct inverse function. So now I can do the same thing I did earlier to check, right? I can compose this with this, and I can compose this with this in both directions. If they come out to be x, then I know that I got the correct function. Right? So I'm going to erase everything other than the functions that I just came up with. So I'll leave the f of x, and I'll rewrite the inverse function. So we got the inverse function. I'm going to call it the inverse function. Even though I haven't proven it yet, I'm going to try to prove that this is the inverse function, which was x plus 1 to the 1/3. So that's what I'm calling my inverse function. So now, just like we did before, I'm going to compose f with what I'm calling the inverse function, and I'm going to hope to get x back if I did everything correctly. All right, so the inverse function now becomes the input to the f function. The f function says take the input, raise it to the 3rd power, and then subtract 1. So I'm going to take that input, I'm going to raise it to the 3rd power, and then I'm going to subtract 1. Now notice here, again, our property of exponents, 1/3 times 3 leaves us with x plus 1 to the 1st. 3rd times 3, we don't see the 1 there, we know there's a 1, minus 1, so we end up with what we hoped to see there. Again, we have to do it in both directions, so now I'm going to take the inverse function of f of x. Now I'm going to use the inverse function definition, and I'm going to use this as the input to that function. Draw a line under here. All right, so now the inverse function says, take the input, add 1 to it, and then raise that result to the 1/3. I'm gonna take the input. I'm gonna add 1 to it and raise that result to the 1/3. As we can see here, we're gonna get x cubed raised to the 1/3. And that gives us what we want to see, the x. So that's going to tell us that we did things right. Right? We did it right. We know we did it right because we checked it in both directions. We found the composition of f with the inverse and got x. We composed the inverse with f of x and again showed that it equals x. So we know the answer we got originally for the inverse function is correct. This is in fact the inverse function to this. Okay, so not all functions are going to have inverse. So that's the last thing we want to discuss. So let's look at a couple of examples. Let's say, well, let's discuss what the horizontal line test is. Horizontal line test. If you recall from previous chapters, the vertical line test was a technique we used to determine whether a relation, a graph of a relation, was a function or not. That was the vertical line test. If we could draw a vertical line perpendicular to the x-axis and it intersected the graph in more than one spot, then it was not a function. If it intersected in only one spot, then it was a function. Going along with the definition of a function where each x input can have at most one output. So let's look at a function, a simple function that we're hopefully all familiar with. Let's say x squared. So if we look at x squared, hopefully we remember what x squared looks like. It's just a parabola with the vertex at the origin. So this is the graph of x squared. Now notice this passes the vertical line test, right? We can draw a vertical line perpendicular to the x-axis anywhere along the x-axis, and it's never going to intersect the graph in more than one spot. So this graph passes what we call the vertical line test, VLT for vertical line test. So it is a function. So it is a function. It fits the definition of a function. But in a similar way, if we draw a horizontal line perpendicular to the y-axis, same rules. We can't do that. If we draw a horizontal line here, notice it crosses the graph in more than one spot. Okay, so this does not pass the horizontal line test. So what we say, so this function does not have an inverse. So this function does not have an inverse. So it does not pass the horizontal line test. It does not have an inverse. If we tried to find the inverse of this function, we would see that we don't get a function. Let's try it. So if we use y equals x squared and we go through the method that we just discussed earlier to try and find the inverse of this function, first we would switch the x's and y's, then we would solve for y. So we would get plus and minus the square root of x. That's not a function, right? Because 1x, if we put x equals 4 in here, we get plus and minus 2. That doesn't fit the definition of a function, right? Not a function. So the horizontal line test tells us whether a function, we're going to introduce a new term here called one-to-one. Functions that have inverses. So a function that has an inverse will pass the vertical line test. Will always pass the horizontal line test, excuse me. Horizontal line test. And that function is called one-to-one. Okay, so remember for a function, each x, if we think about -2 here and 2 for x squared. -2 and 2 both give the same output. That's okay. That fits the definition of a function. Right? Each input can have at most one output. But a one-to-one function, now we have to go in both directions, X and Y. Each Y can only have one X. So a one-to-one function, this is not. This does not pass the horizontal line test because -2 and 2 give the same output of 4. It's not one-to-one. One-to-one means every one X is associated with only one Y. That's a one-to-one function. If a function is one-to-one, then it will pass the horizontal line test and it will have an inverse. If it doesn't pass the horizontal line test, then even if you try to find the inverse, you will see that you come up with something that is not a function. This is not a function. If you were to draw this, you would see that this does not pass the vertical line test, right? Not a function. Right? So let's look at a function that is one-to-one and does pass the horizontal line test. Such as, let's say, x cubed. So if we let f of x be x cubed, and hopefully we're familiar with some of these basic graphs, x cubed is going to go up toward the positive for the positive x's, but then since it's an odd exponent, it's going to go down on the negative side. This passes the vertical line test, so it is a function, and it passes the horizontal line test, so it's a one-to-one function. So this is a one-to-one function. It passes the horizontal line test, and it does have an inverse. Okay, all of those things. If we try to find that inverse, again, we can come over here and say y equals x cubed. We switch the x's and y's, we solve for y. So we take the third power of both sides, and we would get that inverse function. So x to the 1/3 is the inverse function to x third. If you compose these in both directions, you'll see again that you do get the original input. Okay, so inverse functions. Horizontal line, if you have the picture of the graph, you can perform the horizontal line test to determine whether the function has an inverse or not. If you're given two functions, you can show whether they're inverses of one another by composing in both directions. Given one function, we go through our steps of rewriting in terms of x and y, switching the x and y's, solving for y to get the inverse function. And I think that's it. They're inverse functions, right? Be able to determine whether two functions are inverses of one another, be able to find the inverse of a given function, be able to determine whether the graph given to you passes a horizontal line test and has an inverse function. If it does have an inverse function and it passes the horizontal line test, we call it a one-to-one function. All one-to-one functions have inverses and pass the horizontal line test. All right, thank you very much.